In part 3 of section 5, we're going to be looking at a fifth way of putting two functions together. Now, this is not considered a combination, it's called a composition. It is a type of way of putting two functions together that does not have an analogous representation with just real numbers. So this is not a traditional add, subtract, multiply, or divide. With the combinations we were discussing earlier, you would take the result from F and the result from G, and then you would either add them together, or you would subtract the answers, or multiply the answers, or divide the answers. This is going to be different. We're going to be using the result from the first function, and we're going to be using that as the input for the second function. So this first example is going to help to show a little bit more about what I'm trying to explain here, and then we'll get into the definition and then some other examples later on. But what I want you to see here, it says use the following graphs to estimate the area of an oil slick after 2.5 hours. So the idea here is that oil is being spilled into maybe some kind of body of water, ocean, Gulf of Mexico, something along those lines. And with ideal conditions, and the water is pretty still, there's not a lot of current going on underneath the ocean or within the ocean, then the oil spill creates a circle pattern, and the circle just gets larger and larger and larger as more oil spills into the ocean or onto the water. So these two functions that are being represented graphically, remember there's 4 ways to represent a function. A graphical representation is one of those ways. With these two functions, we should be able to answer this question. So I'll notice that what I'm trying to get to is an area answer, but what I've been given is a time of 2.5 hours. So when I'm looking at these two functions, the first thing that I want to do is look at the horizontal axes. So the horizontal axis for the first function on the left is time, and it gives me a variable of t. And for the function on the right, I'll call this the second function, it has radius on the horizontal and little r to represent that variable or that value. So it doesn't say anything about area with either of these two things, but I do know that I was given a time value. So I'm going to say let t be equal to 2.5 hours. It tells me to use t, and I'll just assign 2.5 for t. So I'll come over here to my graph at 2.5 on the horizontal axis, and then I'll carry that up until I get to the curve, and then I'll carry that over to the vertical axis, and it looks like I'm about at a value of 2. So in other words, I have a radius value of 2. So now I can look at the vertical axis and see what type of calculation I'm getting from that. What type of value do I get from there? And then up at the top, it tells me that this is r of t. So going back to what I'm notating here below the graph, I can then say r of 2.5 is equal to 2 kilometers. So in other words, after 2.5 hours, the radius of the oil slick is going to be 2 kilometers long. But I'm not really interested in the radius. I'm interested in the area. But there is no way that I could have used this second graph without having a radius to start with. So this is what I was getting at. We're going to be using the result from the first function to help us get started with the second function. And that's not the case with the other kind of combinations. You can work with just the first function by itself, and then just the second function by itself, and then you can add the two answers together at the end. You have to do the first function first here and then get over to the second. So now I'm going to take the result that we just came up with, and I'm going to say let r be equal to 2 kilometers. and then there's going to be a result from there. So coming to 2, carry that up to the curve, and then translate that over, and it's an estimate. Without the actual equation in front of us, the graph is only going to be able to estimate for us at best. So it looks like it's 12, 12.5, somewhere in that range. So I would say then that A of 2 is equal to 12.5 kilometers squared. And I really should probably put just an approximation here because I don't know for sure. It's just an estimate. And I know that it's A because up here on the vertical scale it's telling me that it's area, capital A. And that's the that's the end result right there. That's what I'm trying to find. That would be the area of the oil slick after 2.5 hours. Now I can actually take these two results and put them together into one statement. I can say A of R of 2.5. So I can do what's called embedded function notation, or it's a function within a function. So we first did the calculation R of 2.5, which we figured out was 2. And then we took 2 and applied it to the graph of A, capital A, and found that the answer was 12.5 kilometers squared. So we can put it all together there in what we call a composition of functions.